Okay, so it seems it's recording now. So welcome everybody to this new session of the CIMNE seminar course. Today we are pleased to have with us Juan Marcelo Giménez, who is a Severo Ochoa postdoctoral researcher at CIMNE and an adjunct researcher at CONICET in Argentina. Today he's going to talk us about his latest research in the Pseudo-DNS method, a multiscale approach to solve fluid dynamic problems. Juan Marcelo, when you want, you can start. You're muted. Sorry, you're muted. Yeah, thank you.
Thank you, Ignacy. Thank you, Ignacy, for the presentation, and CIMNE and you, Ignacy, for the invitation to talk here. As you present me, I'm Juan Marcelo Giménez. I'm from Argentina. I've been collaborating with CIMNE for the last 10 years, I think, almost the time with the collaboration in the collaboration with Sergio Idelson and his group. Since October, I'm working here at CIMNE with the Severo Ochoa scholarship. So, well, I will be talking about our latest developments about the Pseudo-DNS method. I want to start with the motivation of this methodology. If we want to solve fluid dynamic problems or fluid dynamic phenomena, there are several phenomena that require fine discretizations. Obviously, if we want only to solve the governed equations without any additional modeling, this is if we want to solve the DNS, we want to obtain the DNS solution of the phenomena. For example, well-bounded flows. The typical case is the student case is about the convection diffusion equation, where the Peclet number is higher than 1, considering the elemental Peclet number. We expect a solution like the left, but if we use a coarse mesh, we will obtain a solution with some numerical instabilities, which completely destroys the numerical approach. Another phenomena that requires fine meshes is the treatment of boundary layers in the flow, where we want to simulate the transition between the free stream reference velocity out of the boundary layer up to the non-slip condition over the wall. The transition is in a very narrow space in comparison with the global scale of any problem. So the computational requirement here is large also. Turbulent flows is the most typical case, where we have a global scale dominated with the main structures of the vortex and instabilities, up to the Kolmogorov scale, that is the smallest scale that the turbulence appears. The smallest is linked with the smallest vortex, or the scale where the energy dissipates. The range between the largest and the smallest scales is very wide, and depends on the Reynolds number. So a complete resolution of all the energy cascade is only available with a small Reynolds number. Another problem is the treatment of heterogeneous fluids or multiphase flows, for example, where we want to solve some problem at macro scale, in the right side of this picture, where we want to compute some quantities at device or equipment scale. But if you don't include any modeling, we have to solve the movement of each of the components of the dispersed phase, for example, particles or some features of the material that living in the microscale. So we need also very fine meshes. Our idea with pseudo-DNS numerical simulation, P-DNS, is obtain a numerical methodology to overcome the computational burden associated with direct numerical resolution of governing equations. We want to solve any scale, but with a smart approach. Well, Pseudo-DNS is a multi-scale, the main concepts. I will tell you 4 main concepts about Pseudo-DNS. Pseudo-DNS is a multi-scale approach. The unknown fields are separated into meshes. We call it the coarse mesh and the fine mesh. So we solve the problem in a coarse and a fine mesh. But instead of solving all the fine mesh, we split the fine mesh solution in many separated subproblems. We call it RBEs, taking some ideas from the study of composite materials. But I think the main advantage of pseudo-DNS is that the RBE solutions are computed in a pre-process, in an offline computation, because we solve the RBE for dimensionless parameters. I will show you in next slides more about that. This pre-compute or this offline process allows us to construct synthetic models representing the microscale or the fine scale to perform coarse scale simulations. So the main concept is that we perform several simulations for dimensionless parameters in a offline simulations in a fine scale. We construct some fine scale synthetic model and finally, when we want to solve a coarse scale or a global problem, and we require the data from the fine scale, we just consult the fine scale synthetic model, passing some dimensionless parameters and receiving some dimensionless data. Well, I'm going to apply this methodology for the simplest problem, the convection diffusion problem. I will try to explain for those that don't know about pseudo-DNS how this method works. We start here with the convection diffusion equation, and we are going to propose a splitting of the unknown into a coarse solution and a fine solution. The coarse solution is a linear approximation of the total phi function, and the fine solution complements the coarse solution to obtain the full solution. Inside any element, I think that the coarse solution is a linear function, and phi f accomplish some requirements. In particular, for convection diffusion, we are going to require that at the node boundaries, the fine solution will be null. We can rewrite this requirement as in this expression where the average of the gradient of the fine solution is null. Well, I leave it here, this result, because we are going to use next. We introduce the splitting in the convection diffusion equation, obtaining a new equation. And now we are going to use two superimposed meshes, a coarse and a fine mesh, where that shape functions allows us to obtain the value of the unknown as a weighted average of the value of the unknowns at on the nodes of the coarse mesh and the value of the function on the nodes on the fine mesh. So introducing this linear function, the supraindex C is coarse for the coarse mesh and the supraindex F for the fine mesh, we obtain this equation system where we found an equation for the coarse mesh, the first one, and the second one, an equation for the fine mesh. If we pay attention on the equation of the coarse mesh, we see that appears two terms relating the solution, appears two terms in the coarse mesh equation, which requires information from the fine scale. One term regarding to the convective term and another term regarding to the diffusive process. For simplicity, we are going to consider diffusivity and velocity as constant, and we can rewrite those terms as here, but because we have chosen a particular choice of the fine scale solution, we have seen that the mean of the gradient is null, so the second term is null, and finally, the coarse mesh equation leads as presented here. I rewrite here the same equation. We see that the coarse mesh equation is the same for any weighted average or weighted residual procedure with the advective term, the convective term, and an extra term regarding to the information that we need to compute in a fine scale. So, how to compute the information or the integral here in the fine scale? Well, this is the main scheme. We have per element a linear solution on the coarse scale, and we want to compute the fine solution at this element. Instead of solving this problem with an arbitrary edge, an arbitrary diffusivity, an arbitrary gradient, we are going to solve the same problem. Same problem means we are going to use the same Peclet number but solving in a parametrized space, and a space which have length 1, diffusivity 1, gradient of the linear function 1, but varying the velocity according to keeps the Peclet number. Because this solution is using dimensionless parameters, we can compute as many solutions as we want in an offline process to construct a kind of response function about the fine scale. So we are going to solve several simulations varying the Peclet number, and we are going to obtain in each simulation a value tau. Tau is the integral of the fine scale solution. And instead of computing, therefore, instead of computing the convective diffusion equation per element, we are going to just consult the RBE result function. Because we have solved in a dimensionless space, we must not just use the value tau, we also have to include some rescaling factor, but it's just a scalar product. Well, so we introduce in the coarse scale equation this term, and we finish with the methodology. So we have an online solution in a coarse scale, offline solutions in a fine scale, and some synthetic model, but here is just a 1D curve, a function which depends only on the Peclet number of the element, and some dimensionless data that is exchanged between the scales. Well, we test this convection diffusion approach using Pseudo-DNS in a problem with a high Peclet with a coarse mesh. The same problem that I showed you at the beginning of the presentation. The solutions are very good for different Peclets, for different refinements of the coarse mesh, not just for uniform sizes. This figure maybe synthesizes very well the solution obtained. The convergence of the methodology is inherited from the coarse and fine scale solutions, because we have solved the fine scale and both the fine scale and the coarse scale using second order accurate discretizations. The global convergence of pseudo-DNS is also second order. It's second order for both refinement for the coarse scale. It means the number of elements used in the coarse mesh, and the number, we have a second order convergence also for the number of elements that we use in the fine scale. We can choose how we want to obtain more accurate results. Maybe spending more time in the offline process, or spending more time in the online process. Well, this is an overview about applying pseudo-DNS. I will not show more equations, maybe. Yeah, well, we applied the same procedure to solve the Navier-Stokes equations for homogeneous flows. In this case, we have to split the two unknowns, the velocity and the pressure. We introduce the splitting in the Navier-Stokes equations, and using some hypotheses and some filtering, the coarse scale equation reads as shown here. It's the same equation that we usually solve in any problem, but we now include here an extra term which depends on the product of the velocity in the fine scale. Sorry. Well, we call it sorry. Okay. The extra term I said that depends on the product of the velocity in the fine scale. This is a tensor, means for the fine inertial stresses. Is an average on the RBE of the mean of the product of the velocity in the fine scale. So we must compute this data from the fine scale simulations, and with this target, we construct this RBE. An RBE that is a cube, a three-dimensional cube, where we have parametrized some parameters. We fix the size equal to 1, the viscosity, kinematic viscosity equal to 1, and we have discovered that the inertial stress tensors depend just only on the some dimensionless value regarding to the velocity gradient. Moreover, if we apply some rotations about to the velocity gradient, we can obtain this configuration of dimensionless parameters that were means for a pure shear stress problem. This means that we are going to have only two dimensionless parameters that rules the behavior of the fine scale, the ID1 and ID2. We apply some periodic boundary conditions to accomplish some requirements to the fine scale solution. And I here show you some particular solution where we apply shear stresses. At the beginning, there is not instability, but in some moments, the instability occurs, the flow turns very chaotic, and this is an undeterministic flow, so we can't compute a final state. Instead of that, we are going to solve for a statistical convergence state. So we are going to compute some quantities at the equilibrium. Means for equilibrium some time average convergence. Well, so we are going to compute this tensor, the product, the average spatial average of the velocity, fine velocities, but integrating in time to obtain convergence statistics. We are going to store in our database not this output, because we want the dimensionless value, so we are going to store some dimensionless data. If we perform this kind of simulations for a wide range of ID1 and ID2, we can construct this kind of curves where ID versus some component of the output is shown here, varying ID2. But this response surface can be synthesized using, we propose to use artificial neural networks to model the response of the RBE and to favor the computational implementation of the fine scale resolution. As I told you, we just can compute in the RBE, in this fluid RBE, equilibrium data. Well, the pseudo-DNS scheme for homogeneous flow is here briefly shown. In the fine scales, the offline simulations, we use a standard FBM solver nowadays. And in the coarse scale, we are using, usually we use a solver like a PFBM from particle finite volume method. That is a PFM2 based solver, but using finite volumes instead of finite elements, and is implemented in OpenFOAM. All the methodology here present are implemented in OpenFOAM. So the coarse scale sends to the fine scale the ID1 and ID2 and receives the 6 components of the stress tensor. Because a particular detail about the methodology, because we compute at the RBE the equilibrium stress tensor and the turbulence has C history, we use a kind of a memory model to obtain the current stress tensor as a weighted average between the previous stress tensor and the equilibrium stress tensor. How to obtain the value M? Well, it's a discussion that I'm not going deep here, but I will show you some numerical example where the solution is very accurate. The kind of problem that we are going to solve is the decaying of homogeneous isotropic turbulence. It starts with an initial solution that if you represent it in a very fine mesh, the energy source is deactivated and the energy starts to decay. And the target here is to reproduce the DNS solution or the DNS energy decay solution using coarse meshes. Using our memory model and the pseudo-DNS full methodology, solving the same case in very coarse grids from 32 to 4 at cube elements, we can compare the black lines are the DNS solution and the red lines are the different pseudo-DNS solution with the different grid refinements. And in blue lines, you can see that some LES solution using the same grids. You can see that Pseudo-DNS can reproduce the same energy decay than DNS, but using very coarse mesh. But LES can reproduce the same decay only if you use the fine mesh with 32 cells. With coarse grids, LES gives inaccurate results. In a more complex problem, we have applied this Pseudo-DNS methodology. It consists in the backward-facing step, a very known benchmark. For central Reynolds, we are using a Reynolds of 5,000. The flow is fully turbulent, as I show here, but we have experimental data and DNS reference to compare. We test using a coarse mesh, a coarse mesh of 140,000 cells, and the target is the prediction of mean quantities using this coarse mesh, and comparing between a solution of Pseudo-DNS and a solution with less. The main quantity that usually here is compared is the mean longitudinal velocity at different locations, distance from the step. So I show here some velocity profiles. In black, there are the DNS and the experimental references. And I like to highlight the prediction about the reattachment point. So the DNS predicts really well the reattachment point and velocities near the floor, but LES so predicts the reattachment point, and the difference are here shown. If we look about other quantities, for example, the friction coefficient and the mean pressure coefficients, conclusions are similar. Pseudo-DNS obtains a better agreement with reference data than LES using this coarse mesh, obviously. Well, here I highlight that when the friction coefficient is 0, we can detect the reattachment point, and the Pseudo-DNS is very accurate in the prediction of that quantity. If we see about the turbulence data or the turbulence quantities, for example, the mean perturbations in the longitudinal, transversal, or vertical directions, the conclusions again are similar. Pseudo-DNS is closer to the DNS or the experimental data than LES solution. Well, with these encouraging results, we now are turning our attention to the solution of heterogeneous flows. In particular, we are dealing with multiphase flows. We start with the most, maybe the most classical multiphase flow is the system of water droplets in air. So we have to propose an RVE containing particles. So here I itemize some items regarding to the strategy. The idea is to solve an pure shear stress RVE, but including particles. These particles are considered as a spherical, using the Lagrangian point approach, where the particle is smaller than the size of the element used for the fine mesh. We suppose that we are in a two-way coupling approach because the suspension is dilute. We are ranging in between 1 and 1,000 parts per million in a volumetric concentration. We are going to consider drag forces to the particle, periodic condition for the particle, some distribution for the particle sizes. We are using Rosin-Randler. When the number of particles is large, we employ the concept of parcels to reduce the computational cost. And there we have this shape, if you want. The pure shear stress induces instabilities. The instability could be increased or decreased because of the presence of the particle. And this is the main difference between the unladen or the free particles-free RV. The turbulence can be modulated by the presence of the particles. And the results, well, after going to the results, I will show you some summary of the simulations that we have performed on the RV. We have performed varying the 6 parameters, the dimensionless parameters that now consist the RV in a mesh with that number of cells. We have performed around or more than 800 simulations, considering a cost of 48 hours core per simulation. We have a computational burden of around 40,000 hours of simulation to construct our database. We have performed that kind of computational task. In each simulation, we have computed again the stress tensor for the carrier phase. We store the dimensionless value, and we also compute some indicator for the particles, for example, the mean velocity for the particle or the mean force of the particle phase. And here are some examples about how the RV looks. And this is the highest concentration, around 1,500 parts per million, using the largest diameter considered for this study. This is another case where we use a lower concentration. And the comparison here shows that if we compare with the unladen case, this is the RV without particles, where we have imposed the same shear stress. This is the same ID1 and ID2 values. If we compare, we can see that for low concentrations of large particles, the turbulence results of, for example, the kinetic energy produced in the RV is the same, but when we reach some higher concentration using these large droplets, we can see that the particle-laden RVs, we can see a turbulence enhancement or more production of kinetic energy. This is the so-called turbulence modulation. So the presence of particles induce more kinetic energy. This is, I repeat, with large droplets and large concentration. Instead, if we use similar concentration but small droplets, when I say small droplets, regarding large droplets, I'm talking about 1 order of difference in the size. The situation is different. Comparing with the unladen RV data, we can see that the presence of small particles dissipates the turbulence. So instead of enhancing, we have shown here, or we perceive an attenuation of the turbulence. This complex behavior depends on the concentration, on the particle sizes, on the shear stress conditions. So depends on many parameters that we have condensed on this fine scale synthetic model again. So we apply the same methodology, fine scale simulations, a fine scale synthetic model, and dimensionless parameters and dimensionless data to relate the coarse scale simulation and the fine scale simulation. So I'm just finishing. This is the methodology for heterogeneous flow. Now the dimensionless parameters to feed the fine scale are 6 and 6 output data. Now is justified the use of artificial neural networks because we have several inputs, several outputs. And we use this Pseudo-DNS methodology in the very first case, that is the particle-laden Poiseuille flow in a turbulent regime. We have simulated the unladen case and the laden case using first obtaining a DNS solution in a very fine mesh, about 3 million cells. In the unladen case, and the red lines, the laden case with particles is the blue lines. And the main concept here is that the presence of particles change completely both the flow rate and the mean profile of the velocity. And the only methodology that with a coarse mesh is able to follow the sense of the change of the DNS solution is Pseudo-DNS. You can notice, for example, that using a standard K-epsilon approach for the turbulence, the solution in the unladen case and the laden case is the same. There is not sensitivity using a K-epsilon approach. An LES approach using a coarse mesh is a very inaccurate solution. Coarse mesh, I'm talking about 12 elements in the width of this channel. LES solutions are really wrong in that coarse meshes. Well, this is all. This is a work in progress. I want to mention some collaborators here in the work team. Someone from CIMNE. I'm working in the group of Eugenio Oñate and Sergio Idelson, so they are the head of this research. I'm from Santa Fe, Argentina. I'm working also with. We are working also with people from CIMEC and with people from UADE in Buenos Aires. We have published some works. You can notice that the first work about Pseudo-DNS was published the last year, so it's a very young methodology. So we are very expected about the future of this methodology. Well, some knowledge to the funding sources, and this is all. Thank you for listening.
Thank you very much, Juan Marcelo. It was a very nice presentation. I think we have time for some questions, if any. If someone wants to ask, please write in the chat or open the mic. Okay, Ricardo is wanted to ask something. Go ahead, Ricardo.
Hi.
Hi, Ricardo.
I am a bit curious of something, let's say. This is, in a sense, as I understand, one smart way of calculating the taus, let's say, the stabilization, the subgrid scale parameters, let's say. Very smart way. But what I kind of miss is what is the relation of this with the PFAM, let's say. Where do we need it to be Lagrangian?
Sorry, I didn't listen the last part of your question.
Yeah.
Could you repeat?
What I'm asking is, sorry, I'll switch on my camera. What I'm asking is, at which point do you need the fluid solver to be Lagrangian, let's say? So what do you need to use the P-FLAP?
No, it's not a requirement. It's not a requirement. I said you are mentioned here. I said I said that we are usually using a Lagrangian solver for the coarse scale, but it's not a requirement. We can use a standard Eulerian approach here in the coarse scale. It's not a requirement because it's a tradition of myself and Sergio school, because we know that Lagrangian approaches solve better the convective terms, and we must convect the data, the turbulence data, to carry out the turbulence states. So that's the main reason, but an Eulerian approach can be used also.
But I mean, essentially, imagine that you were not using a particle solver, okay?
Okay.
Then what you have is, let's say, a machine learning based approximation for the green solver within a. That's correct or no?
Yes, it's the machine learning function or artificial neural network is the same. It doesn't care about which solver you use in the coarse scale. You can use the Lagrangian or the Eulerian. You will consult the same database. The chains are here. It's a very tricky thing about how to compute the current stresses, combining the previous stresses and the equilibrium stresses. The previous stresses in a Lagrangian way are convective, and in a Eulerian way we have to convect it without particles, solving an extra equation for the convection of each coefficient. But the artificial neural network or the fine scale model is the same for both approaches in the coarse scale.
But you will have to change equation 17 if you're not Lagrangian. That's what you're saying.
Sorry, I didn't.
Equation on page 17.
Page 17.
The one in just below. You have it. The one in this one. This one would change if your coarse scale is Eulerian.
Yeah. Maybe how to compute the previous state. This is the thing that will change. How to compute the previous state. Previous state means for the history of the turbulence. Maybe it's a tricky thing, but that is the only change.
Question, I think. Okay, thank you.
Okay, thank you, Ricardo and Juan. Is there any other question? Any other person that wants to ask something? If there are no more questions, then let's close up this seminar today. Thank you again very much, Juan Marcelo, for the nice presentation. It was very good. And thank you all for coming today to this new session. And I hope to see you in the next one soon. So, bye, everybody. Bye-bye.
Bye-bye. Thank you, Ignacio, for the invitation. Thank you all for listening.
Thank you for coming, Juan Marcelo.